Hi, I wanted to pick up with the second two items that you picked out for me to work on, June. This first one that I've got written here is a case where you are collecting polynomials. And again, a polynomial is an expression that has a variable term in it, and they're separated. Each of these terms are separated by plus or minus signs. And so you might be given something like this. Either you're asked to come up with a sum, or you might be asked, this first expression represents the number of units that can be produced at manufacturer one, and the second one represents the units that can be produced at manufacturer two, and you're asked, how many in total? Well, you would know that you would set this up as a summing problem then when they ask for the total. So I've kind of, I listed them exactly the way that you gave them to me. And so basically it means that you are collecting like terms. So I wrote that phrase down. You're going to be collecting like terms, and that means you've got them stacked perfectly. They're stacked in like terms. So I would be collecting these items here. So the way I've circled it, and I'm sorry that the minute I get my hand in and out of here, it goes fuzzy. So I'm collecting a positive 4 and a negative 2, and so that's going to be positive 2, those integer rules that we talked about the other day. 6x, x can represent apples. God knows what x represents. We don't know. It's some unknown number. But 6 of this unknown number plus 3 of this unknown number is going to be 9 of that unknown number. And then here I've got an expression, a variable squared, and I can only collect that with a variable squared. So I have to remember that this is 5x squared, and I'm summing it with 1x squared. I just wrote that 1 in there simply to remind you that there's at least one of these x squares that we're summing with that 5x squared. So when I collect that, that's going to be 6x squared. So that is our collecting like terms. Now you might have something where you're asked to find the difference of these two, which means I would be taking 5x squared plus 6x plus 4, and I'd be subtracting the second one. Let's say I'm going to be subtracting x squared plus 3x minus 2. That's what difference would mean. This was sum. And I'm just saying, maybe I shouldn't have put that in there. Okay, so if I was finding the difference of these two, you've got to figure out how to subtract that. But I'm not just subtracting the first one, I'm subtracting all of them. So I was kind of reiterating that. And I need to rewrite this. And I need to distribute. This is like saying distributing a negative 1 to each of these. Or I can think of it that I'm subtracting each of these. So subtracting minus x squared, subtracting 3x, and subtracting a positive 2, which would be equivalent to adding a positive 2. So another way to look at that is you're distributing a negative 1. Negative 1 times x squared is x squared. Negative 1 times 3x is negative x. And negative 1 times negative 2 is positive 2. And then I would be collecting. And so 6 minus 3 would be 3x, and that's going to still be positive. 6 minus 3 is still positive 3. And then here I'm subtracting this, which is going to be 4x squared. So this would represent the difference of these two, and this would represent the sum. I kind of did more than what your problem asked for, but I wanted to demonstrate something that was somewhat similar to that. And then the other thing that's really similar to what you were talking, or what we're talking about up here is, here we were looking at adding, here we were looking at subtracting. What do we do? And then down here, we're asked to multiply. So when they're slapped up next to each other, that indicates that I have to multiply everything in this first set of parentheses by everything in this second set of parentheses. That's going to mean, I always kind of draw this on here. I call it rainbows and scoops. So just to kind of remind me that I have to take 5x and multiply it by the first item, 5x and multiply it by the second item. And then I'm going to take 7 times the first item and 7 times the second item. So again, I call it rainbows and scoops just to make sure that you don't forget them. Some people call it FOIL, first, outer, inner, last, and I think everybody gets kind of, I don't know, rainbows and scoops is more fun. Okay, so 5x times 3x squared, that's where I'm saying 5 times 3, I know what that's equal to. That's my whole number multiplication. That's going to be 15. But x, there's like a first power here. So x to the first power times x to the third power. So x times x squared would actually be equal to x times x times x, because I'm multiplying it times itself that number of times. So that would be 5x to the third power. So this is those exponent rules when you're multiplying. And then I need to take 5x to the first power times 2x, which is going to be, again, we know that 5 times 2 is 10. And then x times x is going to be x squared. Now I need to take the second item. 7 times 3x squared is going to be 21 x squared. And 7 times 2x is going to be plus 14x. Now notice, I had to keep these exponents because I wasn't multiplying by an exponent here. Okay, so now we look at this and we've got 4 terms. So 2 times 3 terms, or 2 terms times 2 terms gives us these 3 terms, but these are like terms. And by like terms, I mean they have the same exponent. So I can collect those. So this would be 15x to the third plus 31x squared plus 14x. So in this little review, we've talked about summing, subtracting and multiplying. It kind of makes sense that you might want to know about division. I would only do division, worry about division when it was something like 3x squared plus 2x and we were dividing by x. That basically means you're taking each of these terms and you're dividing them each by x. And you know your fraction rules. This x squared is like saying you've got x squared or x times x. So basically when I'm doing fraction rules, I'm reducing an x for an x, an x for an x. So this would reduce to 3x plus 2. I don't think you're going to see that very often on the high set. And when you do, a lot of times you see it, it's much more complicated than this. It's like taking a trinomial and dividing by a binomial. And I don't even want you to mess with that because usually that involves something that's a little higher level. I would call it algebra 2 for sure, if not pre-calc. So I'm going to put that aside. And then the next item that you asked me to do was, I don't even know what problem it was. I think it was this one. I don't know. I got to go look for your paper again. But anyway, this is dealing with simplifying radical expressions. And I guess I wanted to start out and just kind of point out that any variable square, basically x squared or some variable raised to some power is an exponential expression. So, as well as the square root of some other number, that's also an exponential expression. Both of these are exponential expressions. But they sure have different forms, but they're vice versa of each other. Like I can say 2x squared, oops, it's probably not a good one. Let's say 2x to the cube power is equal to 2 times 2 times 2, which would be 8. The reverse of that would be taking the cube root of 8. And so I'm asking myself, this number in here, I need to break it down into factors. And is there any one factor times itself 3 times that is equal to 8? And that would be 2. So the cube root of 8, in other words, what number times itself 3 times is equal to 8 is going to be 2. Now you've done that probably with something like 5 squared is equal to 25. We all know that one. But what if I had square root of 25? I think you probably know that that's a perfect square. In other words, what number times itself is equal to 25? And you know that that would be equal to 5. So these are reverse expressions of each other. But you're noticing there's no little 2 in here. How come I didn't put that little 2? And it's really kind of a misnomer. We really should put a 2 in there to say that we're not talking about the cube root, the 5th root, or the 8th root. We're talking about the square root. We just kind of assume that. If there's not a square in there, we assume it. Just like on that other problem, if there's not a 1 in front of here, we know that it's meaning at least 1 so that we could collect. It's things that we assume. And so that's kind of what I was talking up here, is that when we have the square root of x, that's assumed the second root of x. Well, that can also be communicated as a fractional exponent. Same thing here. If you have the cube root of x, that can be written as x to the 1/3. So I don't have any numbers in here now, underneath here, like I did here and here. Now I've got variables underneath here, and so I'm just trying to find a new way to write that. And so something to fifth root of x, I'm asking, what number times itself 5 times is equal to x. And so that would be x to the 1/5. So in other words, we've got a power that is now a fraction. I've kind of explained this before. We're used to exponents here, where we've got a whole number up here in this exponent. Basically, if you've got a little number here, kind of think of it, it's in the crack there, it goes up here in our denominator. It goes down there in our fractional exponent. So this little number out here is going to go underneath each of these and create a fraction. So this fifth root of x cubed y squared could also be written as x to the 3/5 and y to the 2/5. Got to keep moving here because this is a 15-minute video. This fifth root of x squared y to the 5th could be written as, now again, that little root means it comes down here as a fraction in both of these exponents. So I write it as x to the 2/5 and y to the 5/5 or 5/5. Well, that can be simplified to 1. And I can either write that 1 or not write the 1. So very often you'll see that 1 not written there. It's just assumed that it's there. Okay, so here we've got the third root of x to the 9th, y to the 12th. Well, that means I have to take this 3 and put it down here in the fraction. So I've done that here. And then you get rid of that radical sign. So x to the 9/3 and y to the 12/3 would simplify. Both of these are fractions that can simplify to x to the 3rd, y to the 4th. This is the 7th root of an expression, which just means we're going to put that 7 down here in the denominator. In each of these, well, this first one can't simplify, so I'm going to leave it as is, x to the 2/7. But this y to the 14/7, that reduces to y squared. Sorry. Okay, so what you might be looking here is like, why in God's name do we have, a new way to notate this stuff? And a big thing of it is with computers and so forth, it's much easier to enter this data in terms of fractional exponents than it is in terms of the radical sign here. So that's a big push as we've become more involved in computer programming and so forth, that this has now become a skill that has been put on the high set, and it's expected that high school students might be able to understand that. I'll be honest with you, this is an upper level algebra skill. So again, I don't feel like this is really necessary for you to know, to be sure that you know how to do this, because if you miss this one, it's not a big deal. Just like if you miss a division problem, one of these divisions that is 3x squared plus 7x plus 4, and you're dividing by x minus 3. This is called a binomial. Whereas over here, I was having you just divide by a single term. Here I'm having you divide by, this binomial, 2 terms. That is upper level. I don't think you need to waste your time on that. And in all honesty, I usually don't even teach this to students. It's just not worth the time to try to learn that. But you seem to be such a curious person. You want to learn about everything. And I thought, well, I'll just go ahead and do that for you. But don't feel like you need to know that part. The other 2 problems, I would say for sure, you'd want to check those out.